Okay, so you can watch me comic now. Supposedly, this is working better. I have no idea if that's actually the case. So, if this is not working, I'm gonna have to do something to fix it. Thank you for your patience. I'll try to be kind. I'm gonna start over from the beginning. And I'm gonna cut out a few things that I was gonna say. I'm actually gonna cut out De Morgan's laws. De Morgan's laws are awesome. They're great. Awesome Boolean algebra. Um, let's talk about Karnaugh maps. What is a Karnaugh map? So the idea behind a Karnaugh map is um, if I have a truth table, I've got A, okay, and in my truth table, I know that let's say if I want switch one to be off, switch two to be off, I want this to be on. If I have switch one off, switch two on, I want this to be off. If I have switch one on, switch two off, I want this to be on. And if I have both on, I want this to be off. Okay? I just randomly created this. So now I have a two-switch situation. Two switches operating in tandem create some output that I have control of. Okay? See. Again, I have no idea if my audio is even working, so please let me know if there is an issue. I will try to address it again. Let's say we've got something like this. Okay? On, off, on, off. We can write it in a truth table like this, and this won't tell us how to build the circuit, but it will tell us the truth table. Yes, Walker has provided confirmation. Very good, supposedly. I don't know if that changes. Okay. So here is truth table. We can rewrite this in a different format. I'm going to go ahead and write this as A and B. I'm going to draw A has two possible positions, 0 and 1, and B has two possible positions, 0 and 1. I'm going to draw it as a square. Okay? Here, this is 0 and this is 1. So this square right here represents 0, 0. I'm going to write a 1 there. This right here represents 0, 1. So AB is 0, 1. And that represents 0. This one represents 1, 0. This line right here, that's a 1. And this one represents 1, 1. 1 and 1. Okay? So it's just combining what we have in the table now, putting it all, and now we're showing it in a different way. Okay? So this is A, this is B. A, B together creates this configuration. What a Karnaugh map does is it's a very interesting way of looking at things. Okay? This right here, we have two ones together, and we have two zeros together. In a Karnaugh map, having two numbers right next to each other signifies that there's a relationship. This is represented this is represented by B naught. If B is off, we have two ones here. Okay? So the one thing that unifies these ones are they're all in this column right here. It spans the entire table, regardless of what A is. If B is off, it is 1. If B is on, it's 0. So this truth table, you go back and look at it, the places where you have zeros, you have ones here. It doesn't even no matter what A is. This truth table boils down to B naught. B naught equals C. If B is on, C is off. That's what this column represents. B is on, C is off. So this is just, it's a new way of writing things. A Karnaugh map written as a square, written as a rectangle, is kind of a visual idea of the relationships between the different components we're looking at. We're going to do a more complex Karnaugh map and see if we can continue developing. Let's say I give you a truth table. Your truth table is A, B, C, D here. Because there are 3 inputs, we're going to have 2 to the 3rd entries in our truth table. 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1. Okay? And let's say that we're going to go 0, 1, 1, 0, 1, 0, 0, 1. Ha! Not random at all. Let's take this truth table and put it into a Karnaugh map. Okay, so what I'm going to do is you can make it a tall rectangle, you can make it a long rectangle. I'm used to making a long rectangle. So this side, instead of just representing A, it's going to represent this side. It's going to represent A. Okay, here A has 2 outcomes, 0 and 1. So this has 2 rows. Here, where this one's going to be, okay, we're going to write this a little bit differently. Instead of the way that we have written, where it's 0, 0, 0, 1, 0, we're going to do something a little different. Okay? If we write it this way, this is the way that we wrote out our truth table. This represents a binary 0. This represents binary 1. This represents a binary 2. This represents a binary 3. If we write it this way, what we have is look at these 2 numbers. So this number and this number, one number changes. Okay? We have C turns on. Between these 2 numbers, both B and C change. B turns on, C turns off. And then between these 2 numbers, only one number changes again. C turns on. We go from a 0 in the C position to a 1 position. So again, starting B0, B is off, C is off. C is on, B is off. B is on, C is off. B is on, C is on. And then to go from this one to this one requires both B and C to turn off too. This is not the best configuration. We're going to actually switch these 2 numbers around. Okay? What we have here is now, in this column, B is off, C is off. B is off, C is on. B is on, C is on. B is on, C is off. Between each one of these, we only have 1 digit that changes. Okay? That does make a difference. Only 1 digit changing means that every single pair next to each other has a commonality. Both of these have a B off. Both of these have C on. Both of these have B on. Both of these have C off. Notice there's 0 in the C column. They're right next to each other. The commonality, if we write it in this way, 0, 0, 0, 1, 1, 1, 1, 0, the commonalities are right next to each other. Okay, so this is why Karnaugh maps are a little different than truth tables. The goal of doing this is to take numbers and put them next to each other. So here, this again, B is off. With a 0 in the B column, both of these columns together mean B are off. If I want to signify A, B on, B not, that is very easy for me to do. Okay, A right there. Everything else is 0. Then here is this is your truth table. Okay? That's it. If these two are on and nothing else is on, then it's A, B not. Because A is on, and B is on. Okay? Now we do have a truth table over here that we're going to populate this with. So we'll work on this a little bit. So here, table 1, when A is off column, this one right here, and the C on and B on, we have 1. 1 here, we have 1 here. Okay? Similarly, here, in the on column, they're both off, or they're both on, both B and C off, both B and C on. We have 1 here and 1 here. Okay? Well, that's kind of ugly, but we're going to work with it. Does this one have any connections next to it? Okay, it has nothing in the box over here, nothing in the box over here. What that means is this is kind of an isolated incident. If we want to represent this number 1, we can represent it as A is off, B is off, C is on. That represents this one right here. Okay? So A is off, B is off, C is on. That represents just this one. We're taking care of this one. Here, this one has one above it and a one right next to it. Okay, let's focus on this relationship. And that 2 column right there, what this represents is regardless of what A is, A can be on, A can be off. If B is on and C is off, the value is a 1. This column represents regardless of A, if B is on, B is off, B is 1. Okay? Now, what about these 2 ones, even though they're across the table from each other, they're actually next to each other because, again, only 1 digit change between these 2. B turns off. What do these 2 have in common? Well, in this column, C is off, B is on. In this column, B is off, C is on. The only thing these 2 have in common is that the C position is a 0 in both of them. So C is off. The other thing that these 2 have in common is both of them, A is on. Okay? So this is the Boolean algebra expression for how we can develop this circuit. Okay, we've got A naught, B naught, C, which is this one right here. We have B, C naught, which is this column here. And we have A, C naught, which is these 2 boxes over there. If we add those together, we get D. Okay, now we can take this expression, based on what we did last time, and write it as a logic gate series. So, whiteboard. A naught, B naught, C plus B, C naught plus A, C naught equals D. Okay, so we've got our A, B, C inputs. Okay, we got 1 AND gate here that is A naught, B naught, C. So I'm going to create an AND gate here. And then go up here, go in like that. have you go up here like this, and then you go in like this. There we go. That is A naught, B naught, C. A naught, B naught. Okay, so there's the first term. You got that. Second term, B, C naught. So again, another AND gate because they're multiplied by each other. B, C naught. Jump over this wire, straight in. Take this one, knot it, and now what we have coming out of it, B, C naught. Okay, now we need a third term, A, C naught. So I'm going to take A, jump over this one, jump over this one. Now this is A, C naught. Hey, we probably could have put a knot here. We don't need two of them right there. Simplify this a little bit. Now one less component we need. Make everything easier. I don't know. These are the three components we have. Now to add them together, we include OR gate. This goes in here, this goes in here, this goes in here. And the output is B. This is our logic circuit that we derived from a truth table. Okay? So that's the benefit of using a Karnaugh map is it allows us to come up with this Boolean algebra statement. Once we've come up with a Boolean algebra statement, we can create a logic section out of it. Okay? Drop me a question if that made absolutely no sense, but we're going to do it again. Hopefully it will make more sense, or you'll be so thoroughly confused that you contact me afterwards. One thing with quarantine is away from the ability to in front of me. Learning is suffering. It should be well, enjoyable. However. So let's do a new truth table. This time we have 4 inputs, A, B, C, and D. Okay? And here I'm going to have very specific inputs and outputs. 1, 0, 1, 1, 0, 1. 1, 0, 0, 1. 1. Four, 5. Okay, I have it. Where's my truth table? It is just as massive and ugly as you would expect out of a 4-column truth table. 4 inputs means we're going to have 2 to the 4th entries in our truth table. Okay? 16. 16 entries. Now, we have a lot of 1s in the E column. Yeah, I can see the top of it. Like we did last time where we combined B and C at the top of the table, here because we have 4, I'm going to go ahead and combine A and B on the left side of the table so that AB represents the number of rows and BC represents the number of columns. Okay? So I will create a Karnaugh map. Karnaugh map is going to have 4 columns and 4 rows because we have 4 possible values out of AB, and 4 possible values out of BC. Okay? If we had to include 3 values here, we would have 8 possible values. We'd have to make the table twice as big that way. If we have 3 values here, we'd have to make the table twice as large this way. Here, AB is represented by 0, 0, 0, 1, 1, 1, 1, 0. Once again, we're following the same number categorization that we have here. Okay, 0, 0 represents A naught, and then A naught B, 1, A 1, 1, B naught. Okay, so each time we have this, exactly 1 gate changes. Between these two, B turns on. Between these two, A turns on. Between these two, B turns off. Between these two, top and bottom, A turns off. So there's a commonality in at least 1 gate in every single one of these. Okay? The method of going through this is called gray code. That was actually provided in your textbook. I didn't memorize gray code. There is gray code set up for huge amounts of things. Gray code is pretty awesome. Pretty gnarly thing to have. I'm glad somebody came up with it because I don't think I could have come up with that one. 0, 0, 1, 1, 1, 1, 0. Okay. This, instead of representing A, B off, represents B, C off. B off, C on, B on, C on, B on, C off. Okay? So that's how we get our table. We have a total of 16 entries here, which is the same as we have on our truth table. Now we take this and populate it. Now it's going to be easier for me, since I only have 4 zeros here, it's going to be easier for me to populate this by identifying where the ones are not. Because there's so many entries in here. So I'm going to start off with drawing in the blanks, so to speak. And in Karnaugh Maps, it is pretty typical to not include zeros in there. Only ones and blanks. If a blank is blank in a Karnaugh Map, it means 0. If it's 1, it means 1. Okay? That also happens in truth tables. Why people get lazy. It's a lot easier to write a 1 than it is to draw a circle. Sometimes I just put an X. Lots of different ways. But now let's populate this. We're going to identify. So this is C on, D on, A off, B off. So that is over here is 0. I'll erase the 0 and replace it with 1. This is A off, B on, with both of them on. This is 0 here. This one is A on, B off, C on, D off. Okay. On. Apologies. And this one here is C on, B off. C on, B off is this column here. A on, B off. And then the last zero that we have is C on, D off, with both A and B off. That is. Everything else is 1. Let's go ahead and erase those 4 boxes because they are an implicit. There's nothing in the Karnaugh map. Okay. Now we can draw a lot of boxes around these. We can draw a lot of nice squares and rectangles. We can draw this little tiny box. We can draw this little tiny box right here. It's great. But we can capture all 8 of these right here by just boxing all of them. Okay? This box, what do they all have in common? Here, it doesn't matter what A and B is, because it spans all 4 of them. A and B both change throughout these boxes. What doesn't change through these 2 boxes? Off. It's the only thing that doesn't change between these two boxes, but between this entire box. All of those ones have one thing in common, and that is that C is off. And we can draw a box around it, and the box signifies there's a relationship. Since that box covers all of the items where C is off, we can just go ahead and write C not. Okay? Now, adding C not into this captures everything on this side of the table. Okay? Now, we've got two other ones. We have two ways that we can draw this. We can either draw it like this, which is one box at a time, or because these have another ones next to them, we can go ahead and write them like this. It doesn't hurt to overlap your ones. It doesn't hurt at all. In fact, here it's going to make our logic gate a lot simpler. I'll do it again. These two. What do these four ones have in common? Well, let's see. D is on in this column up here, so this represents D on, and this over here represents that A is on. Okay, so this is A. Okay, so the big box here with the 8 ones is C naught. This little box here with 4 ones is D. If we represented that as just 2 boxes, it'd be C on, B off, B off. If you want to represent it as just the 2 boxes, you can represent it as a 4 box. Both of these together. And the thing that this has in common is that B is off. No, sorry. B is off. C changes. And B is on. So you'll notice that now we don't even need a C here. We're going to include all 4. Okay? The bigger the boxes you have, the less terms you have in there. So you'll notice this one only has 1 term. Because this is a box of 8 out of a total possible 16, we've eliminated 3 of the input variables. Okay? Half of the entire thing just represents 1 variable. Since this is a box of only 4, we've eliminated 2 variables. If this is a box of only 2, we've eliminated 1 variable. We're only going to be looking at 1 here. This box here, 1, is represented by D naught. Okay, we're looking at just individual ones at a time. We can add every single one of these ones by writing out their exact code. Okay? It takes a lot of time. It would build you the right logic circuit. You would be able to get that, but it would take you forever. And now instead of only having having 3 AND gates, you would have to have 12 if you wrote all of them out individually as 4-digit cycles. So be aware, the easier, if you can lump, there are words. If you can lump these together in squares and rectangles, nicely and neatly, packets of 2, 4, or 8. It's going to simplify your Karnaugh Maps significantly. It's going to make your logic gates a lot easier. If we're going to write this out, we have our A, so here we have our AND gate together. One of those is C naught. Okay, so now we represent C naught. Inverter goes into the order. I'm going to go ahead and draw it up here. C naught, P naught, we'll go ahead and draw that. Okay, here, like that. Jumps over the C-wire. Here, another gate down here. Now we need one for B not, B not. Okay, I'll take this one, not gate. This one, jump on this wire, go into this output. Not or gate from roll. Okay, so this not too bad, not terrible to build. This a lot harder to build if you were to do every single one of these individually. Put them all on one 16 gate OR gate. Ridiculous. But there's an even easier way to do this altogether. Okay. Now when I wrote this table, I started by writing zeros, 0, 0, 0, 0. Okay. If we identify the zeros, we lump them together. Let's do this with green now. These two zeros and these two zeros are right next to each other. Okay. These two zeros represent C and D on, D off, D off. This one, these two zeros represent D on, D off, A. Okay? But we're not looking at zeros, we're looking at ones. So what do? We invert them. Okay? So we put this in parentheses, we invert it, that equals C. This will give us the exact same output as this. Why? Because we lumped the zeros, everything else is a 1. And we invert the whole thing. After we add them together, we put them into a NOR gate, and we come up with an E. So there is two ways, really, to build every, well, there's 1,000 different ways to build every Karnaugh map. But there's two most efficient ways of doing it. This one only results in 2 AND gates. So here we've even reduced, well, okay, this one only has 2 AND gates. That's about the same complexity. Dang it. So there are times when this is easier, okay? But you can do this. This is completely valid. This gives you the same thing as this. This equals this. And actually, you can use De Morgan's laws and prove that. But I don't want to. So. All right. I'm going to be posting your project for the end of the semester. Basically, what your project is going to be is you need to design a countdown timer. And you're going to be drawing not just the logic gates required for it. You're going to need to draw the truth table for every single number. And you're going to need to figure out how many inputs are needed to get that to happen. And you're going to have to come up with a code to show how do you build a countdown timer. It's unfortunate that you can't be in person because my favorite thing to do is actually physically build these. They're fun to build. You print the cases for them, you put the LEDs on, you put the timer on it, you attach it to your Raspberry Pi, power it, run it. It's a great experience. We can't do that because I can't expect you to have a 3D printer at home. Not everybody has their Raspberry Pis, so this is kind of an unfortunate issue where we can't do the most fun thing, which is this project building countdown timer. I'll try to make up for it by having fun stuff next semester. 50, not taking 50 next semester. False. We'll try to do more fun stuff. I like building stuff. Maybe with this great experience, but knowing that you will not get this experience when you try to make up. You have a homework assignment due tonight. I don't believe you have a reading assignment due tonight. Maybe wrong, but I'm pretty sure it's just a homework assignment. Like I said, I'll get that project posted. That project will be due, I think I'm going to make it May 5th, which is Tuesday. So basically, you have 3 weeks to get your project done. I'll put the details on there, and we can talk about it again in the next lecture. All right. I'll see all of you on Thursday.